Hi, and welcome to another episode of Ordinary Differential Equations. Today we are going to talk about non-homogeneous equations and the method of undetermined coefficients. Let's go ahead and take a look at a mathematical description of this problem. Okay, so what does non-homogeneous mean? Non-homogeneous, as opposed to homogeneous, refers to the presence of a function on the right hand side of your equation. All the problems we have been looking at recently were of the form of a y double prime plus by prime plus cy equal to 0. Now we are changing the problem by throwing in a function on the right hand side. Some function of t is going to be showing up on the right hand side. We are going to limit ourselves to functions that are a mixture of polynomial, exponential, and trig. You remember we call them PET function, polynomial, exponential, and trig, because they provide an easy example for solution steps. There's a description also for other type of functions, but we are going to postpone that for the time being. So what we are looking at is the equation that we had previously, but the right hand side modified to being some function of t. A, B, C are still constants, and f is a PET function. An example of this will be something like this: y double prime plus 5y prime plus 6y is equal to, say, 8 cosine of 4t. And it's possible that the problem comes in with some initial conditions, y0 and y prime of 0. Now, before we dive into all the algebra steps that are involved, let's go ahead and see what is the physical meaning of this. Why are we doing this thing, and what do we gain out of it? That's going to be application that's going to come up later on, but it's good to have a preview of that application so that we know what our effort going to mean in the future. So let's go take a look at the demo. In this demo, you see a spring to which a mass is added. So if my system was just consisting of these two portions, I would have a so-called homogeneous equations. Homogeneous equation, we have solved it already before. Now, the new thing is that we are exerting an external force here. There's a spring that is tied into this pin. This pin is going to go up and down and create a push and pull on this. In this experiment, the frequency at which this pin goes up and down is controlled by this contraption here. So at the beginning, for example, it has a frequency of 1. The objective of this video is to teach about the resonance, that if we go ahead and change this frequency, we see some very interesting effect. At a certain peculiar frequency, we are going to see some wild oscillations. But for most of other frequencies, we don't see much of an appreciable effect. So that's why you see the title of resonance here. So let's go ahead, just take a look at some snippets of this video, and then I put the address of it in the description so that you can go and look at the whole thing at your leisure. So you see at the beginning, we have some minor oscillation while this thing is going up and down. So it's changing the frequency, and this frequency changes, so does the oscillation. Now if we go fast forward a little bit, so by the time we come to a frequency of 3.3 in this experiment, we see that oscillation become wild. Now he increases the frequency and the oscillation becomes tamed again. So that peculiar phenomenon we saw, that at a particular frequency the oscillation was at the highest amplitude, that is the topic of resonance. It's a very interesting issue, and that is also studied in your textbook, and hopefully we are going to look at it in more detail later on. But I just wanted to explain the relevance of it to the problem that we are starting to do right now. Now let's go back to our setup. Our setup is not exact duplicate of what we saw in that experiment. It's just some mathematical example. We go ahead and explain the method of undetermined coefficient in this context. And in the future examples, we are going to have more applications. So what we are trying to solve is this equation. The new thing is that right-hand side is just 8 cosine of 4t instead of being 0. So one important consideration here is that the functions that we are considering on the right-hand side are the pet function. Most important pet function is just sinusoidal, sine or cosine. That's what you saw in that experiment. That's what happens in most applications. But we also make room for polynomial and exponential. The three of them have the property that when you differentiate them, you just get more of pet functions, as opposed to, say, a logarithm or square root or secant or something that when you keep differentiating them, they kind of foam up and sort of get out of hand and all sorts of functions come out. Pet functions are nice in that when you differentiate, you stay inside the family of pet functions. Okay, now what's the method of solution? Method of solution is to break the problem into two pieces. One is to study the oscillations without the presence of the external force and then bring this thing back in. So what does that mean? We go ahead and artificially strip this thing off, replace it back by 0, convert it to the kind of problems we have seen before. So I write it like y double prime plus 5y prime plus 6y equal to 0. We go ahead and get the general solution of this equation. So we just strip this thing off, and we go ahead and solve this. To just flag to ourselves that we are solving a slightly different equation, we call this thing y of homogeneous. So y homogeneous is the solution of this equation. Now we have seen this thing before. You should be able to write down the solution for me in like 10 seconds essentially. So let's see, you take 10 seconds and write down what the solution of that thing is. Okay, and then continue. So you remember what was involved here was to get the characteristic equation. This typically is a friendly equation, so you just go ahead and get the roots of it right away. So I get two roots, r equal to -2 and r equal to -3. Do you remember what we did next? The solution, the general solution of this equation is some multiple of exponential of the first t and the second one. Okay, so that's quick from the previous lectures we had. Now we go ahead and consider the right hand side and then look for a solution of that, not the general solution but a solution. So we go back to the equation. We lower our expectation. We say find a particular solution of this. Anything would do. So we call this one yp for particular. Well, how do we come up with that? And why not start with that right away? We go back to the property of pet functions that their derivatives are themselves. So that's going to give us a lead as to what could be a possible solution of this. In a simple case that we are going to consider first, we are going to consider a so-called family of the function that is on the right hand side. For the sine and cosine, for either of them, the family that we need to consider is any combination of sine and cosine of the same frequency. So I start with the following. I say I'm going to look at the functions that are made out of sine and cosine of the same frequency. It's just that I don't know how many sine and how many cosine. So for take care of that, I write it as some multiple of cosine of 4t and some other multiple of sine of 4t. The reason we are guessing this is a solution is that when I differentiate these things, I just get sine and cosines, and it's very likely that they balance each other out and I'll have a solution, and that's what I wanted. So I just go ahead and differentiate this for my y prime, differentiate again for my y double prime, take all of these things back and put it back into the equation again and figure out what the c and d will be. So that's the reason for the terminology for this lecture. The c and d are what we call undetermined coefficients. And they are going to be found by taking this and plugging it back here and equating both sides and get my C and D. You might be wondering, well, why didn't you call A and B undetermined coefficients? Well, that is some other kind of undetermined coefficient we have dealt before. These things are going to come out of our initial conditions. They don't have anything to do with the right-hand side. In fact, we stripped the right-hand side away to get that. And this new sets of undetermined coefficients are going to be determined by forcing them to match the right hand side. How do we do that? Well, there's a little bit of algebra involved. Let's just go ahead and do it. So I take this thing. I'm going to refer to this thing as just y, so that our writing will be a little bit less. So I need my y prime. So carefully apply the chain rule. A factor of 4 comes out in each case, so I'll have minus 4 c sine of 4t, and then this one will be 4d cosine of 4t, if you want to call it y prime p, just so that we are careful who's who. So y double prime p, so I'm taking second derivative of this or derivative of that one. Another factor of 4 comes out, so it becomes minus 16c cosine of 4t, and then a factor of 4 comes out also a minus 16d sine of 4t. Quickly check that this is a multiple of what you had to start with, and that multiple is minus square of this frequency you have. Now to the next stage. Next stage is to combine these things according to the formula that you have here. What does this formula say? This formula says from y pick 6, from y prime pick 5 of these, from y double prime pick just one of this one. Combine them, add them up, set it equal to that, and you're almost there. So I'd say, let's say one of this, so one of minus 16 cosine of 4t, excuse me, 16c, and 16d, and the 5 of the middle. Now after you do a few of these things, you can abbreviate all of this writing, and then you'll be quick enough so that you don't need to write so much. But the first time around, we're documenting all the steps, not leaving anything out, and that makes it look really longer than what actually is. D sine of 4t. All of this is supposed to reproduce the right hand side for me. That is the 8 cosine of 4t. Okay, now it makes sense to go ahead and carefully collect things. So what do I have? I have some cosines. I have cosine here, I have a cosine here, and some cosine on the right hand side, and then I have some sines. It so happens right now I don't have a sine on the right hand side, but I could have had that one also. When you don't have a sine here, of course it means your coefficient of that is 0. Now let's go ahead, collect all of our cosine in one basket, and collect all of our signs in another basket. And on the right hand side, well, we just have one basket there. So what do I put here? Cosine of 40, I put, of course, this is all the blue stuff. So I have minus 16c, and then plus 20d, and then here I have 6c. Now let's go ahead, collect all the yellow stuff. So I have minus 16d, and then minus 16d minus 20c, and then 6d again. And there's no sign here. That's fine. So let's clean up. I get minus 10c plus 20d cosine of 4t, and then here I get minus 20c minus 10d sine of 4t, and right hand side is 8 cosine of 4t. So let's just remember this is. So what does that mean? It means minus 10c plus 20d has to match 8. And what about this one? What is that matching? Think about it for a second. What is the yellow part doing? That's equal to what? Okay, so I'm sure you immediately came up with the answer. Of course, on the right hand side, I don't have any sign. So if you want to be pushing it, you can say, well, I have 0 sine of 40 here. And that yellow has to match this yellow. So now I have two equations, minus 10c plus 20d, that is equal to 8. And the other one is minus 20c minus 10d, and right hand side became 0. There is a peculiar look to this equation that is a good way of checking your progress so far. It's not accidental that these two numbers are the same. Always turns out this way. And it's not accidental that these two are the same except for their sign. It always turns out that way. So look out for that. If you see something else, it means that you have made some mistake. So how do we go about solving this? Of course, it's a 2x2 system. You have seen this in high school. You do elimination, substitution, Kramer, or whatever you do. For bigger system of this type, we typically use a little software to get by and make sure we are not bogged down in that step of the problem. Right now, 2x2 system is an easy system. So what we can do here is, for example, multiply this equation by 2 and add them up. That is going to eliminate d, and you have minus 10c, and then you have this becomes minus 40c over all is equal to 8 plus 2i 0, that's 8. So it becomes minus 50c is equal to 8. So c is minus 8 over 50. And if you want to simplify, that's fine. Then we take that quantity and put it in either of these equations. For example, here we can see that d is double of c. So d becomes 16 over 50. Okay, so D is minus 2C, and then you find your C and D. So the undetermined coefficients that we were looking for are discovered now. The particular solution that we wanted was C, which is now 8 over 50. That was cosine of 40. And the other one is 16 over 50. I didn't simplify these things, but you could. Typically, there's no simplification that happens. So a solution of this equation, a solution of this thing, is the one we just obtained. Now comes the issue of what's the general solution. General solution, let's write it as YG, G for general, is made out of two portions. One is the homogeneous that you got at the beginning and the particular. So in some sense, homogeneous is the responsive system to itself. That's how it could have been oscillating by itself or moving by itself. And particular is due to the external influences. The solution is split into two parts. And the fact that our equation is linear allows us to actually split the solution into two pieces and add them like this. So what do I have? Y general, or simply just y, is going to be all that we have so far, a exponential of minus 2t plus b exponential of minus 3t. Then I have these new pieces of 50 cosine of 40, and then 1650 sine of 40. Okay, now back to the original undetermined coefficients a and b. How about them? Where do we get them? Once we have the general solution, at the very end we apply the initial conditions. Remember this initial condition always applied at the very end. Common mistake is that the students try to apply it right when they have this. They try to enforce these two. That's incorrect. This is initial condition of the complete solution, not a partial solution. So we come here, say, okay, now enforce initial conditions. Well, for initial conditions, what do we have? We have y0 and y prime 0. So I really need the derivative of this thing too. So y prime, well, differentiate, so I get minus 2a exponential of minus 2t minus 3b exponential of minus 3t. A factor of 4 comes out, so it becomes plus 32 over 50 sine of 40, and then this one also 64 over 50 cosine of 40. Okay, these are the full function. Now what is this thing at time 0? Yg at time 0. Be quickly notice exponentials become 1, cosine becomes 1, sine becomes 0 at time 0. So what is left from this thing is a from here, b from here, minus 8 over 50 from here. Sine of 0 is just 0, so that term falls out. And then this is supposed to be my y0. y0 is the initial condition that they have given to me, so I just take that, and that's equal to 1. Repeat again, y prime at time 0. So from this one I have minus 2a, from this one I have minus 3b, from sine I get 0, from cosine I get this coefficient which is 6450, and that's supposed to be y prime. Y prime is initial velocity. If you remember, y prime was equal to 2. So So again, we have a 2 by 2 system to solve, not any more complicated than what we just looked at. We go ahead and solve this thing. So I have a plus b is equal to 1 plus 8 over 50. So you simplify that perhaps, and again, I leave it to you if you want to simplify. From the second equation, you have minus 2a minus 3b, and that's going to be 2 minus 64 over 50, and that's going to be 36 okay, 2 times 50 is 100 minus 64 is 36 50. 2 by 2 system, you go ahead and solve this thing. So let me just for example, you triple this thing, add to this equation, and then you will have just your a. So a is going to be 3 times this plus this one, and that boils down to 21/5. And same way, you can cancel the a, you double that one, add to this, and you have minus b equal to this number, and you simplify that, and b becomes minus 76 over 50. Okay, then we have our specific solution subject to that initial condition. So I have my a, which was 21/5 exponential of minus 2t, b is minus 76/50 exponential of minus 3t, and then we had our, let's make sure we don't make a mistake here. This was my y, so I have minus 850 cosine of 40, and then 1650 sine of 40. Perhaps to make it cleaner, we can take a common denominator of 76. I think I have a typo here, 76/25, I believe. Sorry for that. So so we get our solution. It's very common in this kind of equation. When you solve, you have some exponentials, and then you have your trig. What do these two portions mean? Best way to look at this thing is to go look at the graph of it on Desmos, and then we get a better appreciation for what is involved here. So let me take you that favorite software of ours, and I've already typed this thing up here. So I took a common denominator so the equation looks cleaner. That is what y of t is. You notice what we see is some kind of peculiar movement at the beginning, and as time passes by, it settles to some sort of oscillation. What's the reason for that? Well, it's quite obvious. These exponentials are going to die away as time increases. So when they die away, all we are left with is our sinusoidal portion. So it's not surprising that the equation settles, the graph settles to this kind of a wave. So in engineering, you refer to the first piece as the transient response, because it just lives for a short time. And then this one will be the steady state response. So some of your problems that are going to ask you, well, what is the steady state response of it? That would be just this portion. If they ask for the transient response, it will be this one. So let's go ahead, note that in our solution here, so the terminology is that this is the transient, because these exponentials make it die away, and this does not die away, and sometimes they refer to it as a steady state. Okay, we looked at one problem, and there are lots of fine prints and things to watch out for in due to presence of two things. One is, well, we looked at a trig function on the right hand side. We gave a recipe that for a simple trig function, our particular function is just a family of that, which is made out of just sines and cosine. Well, what if we had something else, exponential? What if we have polynomial? There are simple recipes for those cases as well. We are going to explore that in the next video. The other issue is a much more profound issue of the resonance. That's more subtle issue. What if we have resonance? What does resonance mean? Well, again, it's something that's intuitive to you. For example, if you have somebody sitting on a swing and you want to push that person, you push that person at a particular frequency. When you do like that, then the amplitude of oscillation increases and the movement is pleasant and it's not jarring. So you choose a certain frequency that has to do with the system itself. That's what the resonance refers to. We are going to look at some particular cases where the right hand side has components which are identical to the components of the solution of the homogeneous. When that happens, we have to go through some additional steps for our solution. I'm going to explain that also in a future video. Okay, so let's wait for the next video. For now, let's go ahead and practice this. There will be several problems on WebAssign for you to do. Until next video, good luck and God bless.